10,
CLS go for main engine start.
6, 5, 4, 3, 2, 1. And booster ignition liftoff of Space Shuttle Discovery, taking the space station to full power for full science.
Space looks simple. That's the first lie. From the ground, the night sky feels open, calm, and inviting. The stars don't move. The planets drift gently. There's no traffic, no terrain, no resistance. To the human eye, space appears like the ultimate empty road. A vast, silent nothing where motion should be effortless. Point a ship in the right direction, fire the engines, and glide forever. That's the intuition most people carry, even subconsciously. So before you get comfortable, take a moment to like the video and subscribe. But only if you genuinely enjoy what I do here, and tell me in the comments where you are and what time it is right now. I always find it fascinating to see our little community scattered across the globe. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. But intuition is a terrible guide in space. The truth is that space is not empty in the way people imagine, and it is not easy to cross. It is hostile, unforgiving, and governed by rules that feel deeply unnatural to the human brain. Every successful journey through space depends not on speed or power, but on understanding those rules and respecting them. The greatest misconception about space travel is that it works like travel on Earth. Cars drive because roads exist. Planes fly because air pushes against wings. Ships sail because water resists their motion. On Earth, movement is a constant negotiation with friction. Push harder, go faster. Stop pushing, slow down. Everything makes intuitive sense. Space strips all of that away. There is no air to push against, no ground to grip, no medium to lean on. Once a spacecraft leaves Earth, it enters an environment where most of the assumptions built into human experience collapse instantly. In space, you don't move because you keep pushing. You move because you pushed once and then never stopped. This single fact changes everything. A spaceship does not travel through space the way a car travels down a highway. It doesn't drive toward its destination. It is not constantly burning fuel to keep moving forward. In fact, most of its journey is spent doing nothing at all. Engines off, systems humming quietly, drifting at thousands of kilometers per hour through an invisible gravitational landscape. And this is where the illusion deepens. When people imagine space travel, they imagine propulsion as the main challenge. Bigger engines, more fuel, higher speeds. But propulsion is only the opening act. The real difficulty lies in navigation, not through obstacles, but through forces you cannot see and cannot escape. Because space is not empty. It is dominated by gravity. Every planet, moon, star, and asteroid bends space around it. These invisible wells overlap, interact, and compete. A spaceship moving through space is not traveling in a straight line through nothingness. It is constantly falling. Falling toward planets, falling away from stars, falling along curved paths dictated by mass and distance. To travel through space is not to fly. It is to fall, carefully. This is why the phrase, heading toward Mars, is misleading. Spacecraft do not aim at where a planet is. They aim at where it will be, and they must arrive at precisely the right speed, angle, and moment, not too fast, not too slow, or they will miss entirely, slingshot away, or crash. There are no second chances in deep space. A tiny error made during launch can grow into a catastrophe millions of kilometers later. A miscalculation of seconds can turn a decade-long mission into a silent, drifting tomb. In space, momentum is unforgiving. Once you are moving, changing direction is enormously expensive. This brings us to the second illusion, that space travel is about going fast. It isn't. Speed feels impressive to humans because on Earth, speed equals progress. Faster cars arrive sooner. Faster planes cross oceans in hours instead of weeks. So naturally we assume the same applies beyond Earth. But in space, Speed is a liability as much as it is an asset. Every increase in speed must eventually be paid for, either with fuel to slow down or with gravity to bleed off energy. Arriving somewhere too fast is often worse than arriving too slow. A spacecraft that cannot decelerate is not visiting a planet. It is performing a flyby. This is why most missions take years, not days. Not because we can't go faster, but because arriving safely requires restraint, patience, and precision. The universe rewards efficiency, not aggression. And then there is the third illusion, that once you're in space, you're free. In reality, leaving Earth's surface is only the beginning of captivity. Spacecraft remain bound by gravity, fuel limits, power constraints, radiation exposure, thermal extremes, and time. Freedom in space is an illusion created by distance, not capability. Consider this. The moment a spacecraft shuts off its engines after launch, it is already committed to a trajectory. That path may last minutes, years, or centuries. Changing it later is possible, but costly. Every correction burns fuel. Every burn reduces future options. Space travel is a game of irreversible decisions. This is why missions are planned years in advance and simulated endlessly. There is no improvisation once you're underway. The margin for error is so small that human reflexes are useless. Computers must calculate trajectories with brutal precision, accounting for gravitational influences that cannot be felt but will dominate the journey. Space is quiet, but it is not passive, and that quiet hides danger. Without air, sound vanishes. Without friction, heat behaves unpredictably. Without atmosphere, radiation strikes unfiltered. A spaceship is not moving through a void. It is moving through a lethal environment where survival depends entirely on a thin shell of engineering and constant energy management. This reality reframes everything. Spaceships do not travel through space the way explorers crossed oceans. They do not venture outward into the unknown with the option to turn back easily. Every mission is a one-way negotiation with physics. The ship does not dominate space, it survives within it, and survival requires humility. Every successful spacecraft ever launched, from the earliest probes to the most advanced missions, obeys the same unbreakable rules. They do not conquer space. They cooperate with it. They borrow momentum from planets. They exploit gravity instead of fighting it. They coast whenever possible. They plan months of silence punctuated by seconds of action. That is the hidden truth behind space travel. It is slow not because we are weak, but because the universe is vast. It is careful not because we lack courage, but because mistakes are final. It is quiet, not because nothing is happening, but because everything is happening invisibly. And this is only the beginning. Because once you understand that space is not empty and travel is not intuitive, a darker realization follows. The very laws that allow us to move through space also impose limits we may never overcome. Limits not of technology, but of reality itself. That is where the story truly begins. Speed feels like the obvious solution. When humans encounter distance, we instinctively try to move faster. We build quicker ships, stronger engines, more powerful machines. From horses to trains to jets, every leap in transportation history has reinforced the same belief. If the journey is too long, the answer is more speed. Space punishes that belief. The idea that spaceships simply need to go faster to reach distant worlds is one of the most persistent misunderstandings in modern science fiction and popular imagination. It feels reasonable. After all, if the stars are far away, shouldn't we just build faster ships? Shouldn't more thrust, more fuel, and more power solve the problem? But rockets are not cars, and space is not a road. On Earth, speed is limited by friction, air resistance, and mechanical stress. Engines fight drag, tires grip pavement, wings push against air. Movement is an active process. If you stop applying force, motion fades away. A car coasts to a stop. A plane falls from the sky. Space erases that entire framework. In space, once you are moving, you do not need to keep accelerating to stay in motion. There is no air to slow you down, no surface to rub against, no friction to bleed energy away. A spacecraft traveling at 30,000 kilometers per hour will keep traveling at that speed indefinitely, unless acted on by another force. This sounds like freedom. It isn't. Because while staying in motion is easy, changing motion is brutally expensive. This is the first great paradox of space travel. Speed itself is cheap, but control is not. You can reach extraordinary velocities with a single burn, but every adjustment afterward requires fuel. And fuel is the most precious resource a spacecraft has. This is where the intuition breaks. People imagine rockets as engines that push continuously, like a jet plane climbing through the sky. In reality, most space missions consist of brief moments of extreme violence, followed by long stretches of silence. Engines fire for minutes, sometimes seconds, and then shut down. The ship coasts for days, months, or years. Why? Because rockets are constrained by a merciless law of physics known as the rocket equation. It dictates that every bit of extra speed requires exponentially more fuel, not linearly, exponentially. This is not a technical inconvenience, it is a fundamental barrier. To understand why speed is not the solution, you must understand how rockets actually work. A rocket does not push against air or space, it pushes against itself. By expelling mass in one direction at high velocity, it gains momentum in the opposite direction. This is Newton's third law, operating with cold indifference. For every action, there is an equal and opposite reaction. The faster you want to go, the faster you must throw mass backward, and that mass must be carried with you from the start. This creates a vicious loop. To carry more fuel, you need more fuel to lift that fuel. To burn that extra fuel, you need even more fuel. Every kilogram added at launch multiplies the total mass requirement. The result is a vehicle that grows rapidly, inefficiently, and dangerously large. This is why rockets look absurd compared to their payloads. A modern launch vehicle may be over 90% fuel by mass. The spacecraft itself, the instruments, the crew, the life support, the cargo, is often a tiny fraction perched atop a tower of explosive propellant. And this is only to leave Earth. Once in space, the tyranny continues. Imagine you want to double your speed. Intuitively, you might think this requires double the fuel. It does not. It requires far more, because the fuel itself adds mass that must also be accelerated. The faster you want to go, the more fuel you must carry, and the more fuel you must burn to carry that fuel. This is why just go faster is not a plan. It is a dead end. The universe does not care how badly you want to arrive sooner. Every additional kilometer per second of velocity comes at a brutal cost. And the cost is not just fuel, it is flexibility. A spacecraft that spends too much fuel accelerating has little left to decelerate. It becomes a bullet instead of a visitor. This is the second great misconception, that acceleration is progress. In space, acceleration is commitment. Once you fire your engines, you are locking yourself into a future that may be impossible to undo. Every burn narrows your options. Every decision eliminates alternate paths. Space travel is not forgiving. There are no shoulders to pull over on, no refueling stations waiting beyond the horizon. This is why most spacecraft do not race toward their destinations. They drift into them. Consider interplanetary travel. Earth orbits the Sun at roughly 30 kilometers per second. Mars orbits at about 24 kilometers per second. A spacecraft traveling from Earth to Mars does not need to catch up in the way a car catches another car. It must carefully reshape its orbit around the Sun. This is the key insight most people miss. When you travel to another planet, you are not traveling to it. You are changing your orbit to intersect with its orbit at the correct time. Space travel is orbital mechanics, not straight-line motion. If you try to go faster in a straight line, you are fighting the Sun's gravity, the dominant force in the solar system. Fighting gravity is expensive. Cooperating with it is efficient. This is why spacecraft follow long, curved paths called transfer orbits. They look inefficient on paper, but they are masterpieces of energy conservation. They allow spacecraft to trade time for fuel, patience for possibility. Speed in this context becomes a liability. Arrive too fast, and you cannot stop. Arrive too slow, and you may miss entirely. This brings us to the third illusion, that braking is easy. On Earth, slowing down is simple. You press a pedal. Friction does the rest. In space, there is no friction. If you want to slow down, you must fire your engines in the opposite direction of travel. That requires fuel, sometimes as much fuel as accelerating in the first place. This is why many probes do not enter orbit around the worlds they visit. They perform flybys instead, not because orbit is undesirable, but because orbit requires deceleration, and deceleration requires fuel they cannot afford to spend. A spacecraft screaming toward Jupiter at tens of kilometers per second cannot simply stop. It must shed enormous amounts of energy. If it cannot, Jupiter's gravity will bend its path and fling it back into deep space. This is not failure. This is design. Engineers often want this to happen. They use planets as tools, gravitational slingshots that redirect spacecraft without burning fuel. By passing behind a planet in its orbit, a spacecraft can steal a tiny bit of the planet's orbital energy, increasing its speed relative to the Sun. This technique has sent probes to the outer solar system that would otherwise be unreachable. But notice the implication. Spacecraft gain speed not by brute force, but by borrowing it. This is the unspoken rule of space travel. Power is scarce. Cleverness is essential. The fastest spacecraft ever built did not achieve their speed by massive engines alone. Bending space-time to move faster than light requires exotic matter and remains theoretical. Could circumvent relativistic limitations if possible. Each method carries trade-offs. High thrust often requires enormous mass and fuel. High efficiency often means low thrust and slow acceleration. External propulsion reduces mass but increases complexity. At interstellar scales, every option is constrained by physics, engineering, and economics simultaneously. Given light-year distances and multi-year delays in communication, interstellar spacecraft must navigate autonomously. AI systems would analyze sensor data, detect hazards, adjust trajectory, manage power, and repair systems. Human crews, if present, would serve as supervisors, but the spacecraft itself would need intelligence sufficient to operate independently. Autonomy also extends to problem-solving under uncertainty. Star systems are dynamic. Radiation bursts, micrometeoroids, and cosmic events are unpredictable. Human intuition cannot intervene in real time. Advanced systems capable of learning, adapting, and improvising would be essential. This transforms spacecraft from passive machines into semi-independent explorers capable of survival in a hostile environment. For crewed missions, life support adds another layer of complexity. Interstellar travel may require decades or centuries, even with relativistic effects. Systems must recycle air, water, and food indefinitely. Shielding against radiation and micrometeoroids must be reliable for the entire journey. Psychological resilience becomes critical. Isolation, confinement, and time dilation pose profound challenges. Interstellar missions are not just engineering feats. They are exercises in sociology, psychology, and biology on a scale never attempted before. Communication delays are unavoidable. Even light-speed signals take years to traverse interstellar distances. A probe sending data from Proxima Centauri would arrive at Earth 4 years after observation. Commanding a crewed starship across light years is impractical. Autonomy and pre-planning dominate mission strategy. Interstellar travel forces humanity to rethink command and control. Decisions must be made in advance. Failures cannot be corrected in real time. Exploration becomes a negotiation with the universe itself. At relativistic speeds, even interstellar gas can be lethal. Radiation from cosmic rays increases with velocity. Micrometeoroids pose catastrophic risks. Long-duration missions may encounter unexpected phenomena, rogue asteroids, uncharted planets, or stellar debris. Spacecraft must be robust, redundant, and self-repairing. Every design choice is a trade-off between mass, energy, safety, and mission objectives. At interstellar distances, mistakes can be fatal and irrecoverable. Interstellar travel is not only a technical challenge, it is an economic and political one. The cost of building, launching, and sustaining a multi-generational or relativistic spacecraft is astronomical. Missions require unprecedented cooperation, funding, and vision. No single nation can currently support a crewed interstellar mission alone. Collaboration, long-term investment, and societal commitment become prerequisites. Interstellar travel is as much about civilization's endurance as it is about propulsion. Finally, interstellar travel challenges our perception of time, mortality, and purpose. To embark on a journey where centuries may pass, where Earth may become a memory, where the crew may never see family again, is to confront the vastness of existence. Interstellar travel is not merely engineering. It is a meditation on humanity's place in the cosmos, a confrontation with scale, isolation, and ambition. Those who dream of the stars must grapple not only with physics, but with philosophy. Despite these obstacles, humanity's ambition is relentless. Small-scale interstellar probes, powered by laser sails or ion engines, are feasible within decades. These unmanned scouts could reach nearby stars in a human lifetime, sending back data, images, and insights. They serve as proofs of concept, testbeds for technology, and first steps toward eventual crewed missions. Crewed interstellar missions remain a centuries-long vision. They demand breakthroughs in propulsion, energy generation, life support, and societal commitment. Yet even these distant dreams drive innovation today. Concepts developed for interstellar travel influence planetary exploration, deep space habitation, and propulsion within our solar system. The pursuit itself advances technology, understanding, and perspective. Interstellar travel is a story of limits. Speed, energy, distance, radiation, and human endurance all impose boundaries. But it is also a story of drive. It is the persistent challenge of navigating the universe on scales that dwarf human experience. It is a negotiation with physics, a confrontation with scale, and a testament to ambition. Humanity may not yet cross the stars, but the pursuit defines the trajectory of our species. Each breakthrough, each probe, each conceptual design is a step across the void, a testament to the audacity of exploration. The stars are distant, the journey is perilous, but the desire to reach them is, in itself, a defining characteristic of civilization. Interstellar ambition forces us to confront physics, mortality, and scale. It demands ingenuity, patience, and vision. And in the process, it teaches us what it means to navigate the universe, both physically and philosophically. The journey may take centuries, the obstacles are vast, but the first step, as always, begins with understanding the void, respecting its laws, and daring to move forward despite them. It is that traveling through space is not merely a matter of speed, thrust, or trajectory. Beyond propulsion and navigation lies the deeper, more fundamental challenge: sustaining life itself. The human body, mind, and society are adapted for Earth's gravity, atmosphere, and ecosystem. Remove these constraints, and survival becomes a series of relentless battles against physics, biology, and isolation. Interstellar travel is not just an engineering problem, it is a problem of existence. Space is an environment designed to kill life as we know it. There is no atmosphere, no breathable air, no pressure. Temperatures swing between extremes, radiation constantly bombards every surface, and microgravity begins to erode bones, muscles, and cardiovascular systems within weeks. To survive, humans must carry Earth with them. Air, water, food, gravity, everything must be supplied, recycled, or artificially simulated. Even microgravity alone presents profound challenges. Astronauts on the International Space Station experience bone density loss at rates of up to 1% per month. muscles atrophy. The heart adapts to pumping in a weightless environment, which can cause long-term cardiovascular problems. Fluid shifts lead to vision impairment. These are not minor inconveniences. They are fundamental biological reactions to the absence of gravity. Extended missions to Mars or beyond require countermeasures, exercise regimens, resistance machines, and possibly artificial gravity through rotation or acceleration. Radiation presents another invisible but lethal threat. Beyond Earth's protective magnetosphere, solar winds and cosmic rays penetrate spacecraft hulls. Long-term exposure increases cancer risk, damages the nervous system, and threatens reproductive health. Solutions exist: thick shielding, water walls, magnetic fields, but every kilogram of protection adds mass, increasing propulsion requirements. Space is not merely empty, it is an environment that punishes neglect. Temperature extremes are equally brutal. In direct sunlight, surfaces can reach hundreds of degrees Celsius. In shadow, they can plummet to near absolute zero. A human cannot survive direct exposure. Space habitats must maintain controlled, stable temperatures. Thermal regulation is a constant battle, requiring active heating, cooling, and insulation. Energy, again, becomes the currency of survival. Physical challenges are only one part of the problem. Psychological resilience is equally critical. Isolation, confinement, and distance from Earth create mental stress that can be devastating over months, years, or decades. Astronauts on long-duration missions report sleep disruption, irritability, and cognitive strain. Interpersonal conflicts can escalate in confined quarters. Even minor mistakes in judgment can have catastrophic consequences in space. In the context of interstellar missions, psychological stress is magnified. Not because coasting doesn't work, but because humans are not built for waiting in silence. Still, the principle remains. The universe does not reward effort. It rewards alignment. A spacecraft aligned correctly with physics needs very little force to travel vast distances. One misaligned burns itself dry. This principle extends beyond propulsion. It defines how spacecraft orient themselves, manage heat, generate power. Solar panels are angled, not forced. Antennas are pointed, not shouted through. Systems are optimized for efficiency, not intensity. Space is an environment where excess is punished. Every watt matters. Every gram matters. Every decision echoes for years. This is why space travel feels so fragile. Not because it is poorly designed, but because it is tightly balanced. The margin between success and failure is narrow because the universe demands precision. And coasting sits at the heart of this balance. To coast is to accept that the journey is already in motion, that the future has been set in motion by the past. That control is exerted sparingly, intentionally, and with respect for consequences. This mindset is deeply alien to how humans live on Earth. We are used to constant correction, constant effort. Space demands restraint. It demands trust in preparation. This is why astronauts often say the most intense moments of a mission are launch and arrival. Everything in between is waiting. Waiting while hurtling through space at unimaginable speed, doing nothing, changing nothing, because everything is already unfolding exactly as planned. And when arrival comes, it is sudden. After months of silence, a single burn decides success or failure. A few minutes determine whether the spacecraft enters orbit, lands safely, or misses entirely. The coasting ends. The reckoning begins. And this brings us to the next truth. Coasting works because gravity is predictable, but gravity is also powerful. And when used deliberately, it becomes the most effective engine ever discovered, which is why the real highways of space are not built with metal and fuel, but with mass and motion. That is where the journey leads next. Humans think engines move spacecraft. They don't. Engines are brief interruptions. Gravity is the road. Every spacecraft that has ever crossed the solar system has done so not by overpowering gravity, but by submitting to it. The planets are not obstacles scattered through empty space. They are anchors, accelerators, and signposts. They shape motion so completely that ignoring them would make space travel impossible. This is the truth that overturns every cinematic image of spaceflight. The fastest, farthest journeys ever made were not powered by engines, but by falling, deliberately, repeatedly, and with precision. Gravity is not just something spacecraft fight against when leaving Earth. It is the primary tool used to move once they are free. And the moment you understand that, the solar system stops looking like a void and starts looking like infrastructure. From a distance, gravity feels weak. On Earth, it is easy to underestimate. You lift a cup, you climb stairs, you jump. Gravity feels manageable, almost trivial. But that intuition collapses at scale. Gravity does not need to be strong to be dominant. It only needs to be constant. Across millions and billions of kilometers, even small gravitational pulls accumulate into decisive forces. Planets do not merely sit in space. They drag space-time around with them, carving invisible valleys that spacecraft inevitably fall into if they pass close enough. These valleys are not hazards. They are opportunities. This is why the most powerful propulsion technique ever discovered does not involve fuel at all. It involves timing. The gravity assist, sometimes called a slingshot maneuver, is the clearest demonstration that gravity, not engines, is the real highway of space. The idea is deceptively simple. A spacecraft approaches a planet on a carefully chosen trajectory. As it falls toward the planet, gravity accelerates it. As it swings around and escapes, it carries that speed with it. But the real magic happens because the planet itself is moving. Planets orbit the Sun at tremendous speeds. Jupiter, for example, travels at around 13 kilometers per second. When a spacecraft passes behind a planet relative to its direction of motion, it can steal a tiny fraction of that orbital energy. The planet slows down by an immeasurably small amount. The spacecraft gains enormous speed, no fuel burned, no engines fired, just gravity doing what it always does. This is not a trick. It is conservation of momentum, executed on a cosmic scale. Without gravity assists, many of humanity's greatest missions would have been impossible. Voyager 1 and 2 did not have engines powerful enough to reach the outer planets on their own. They relied on a rare planetary alignment, using Jupiter, Saturn, Uranus, and Neptune as stepping stones. Each encounter bent their trajectory and increased their speed. Each planet handed them forward, deeper into the solar system, like runners passing a baton. By the time Voyager 1 left the influence of the Sun, it was traveling faster than any spacecraft before it, not because of thrust, but because it had fallen past giants and escaped with their momentum. This reframes space travel completely. Instead of imagining spacecraft as active agents forcing their way through space, it is more accurate to see them as leaves carried along a gravitational current. The current is invisible, but it is always there. And those who learn to read it can go very far with very little effort. But gravity is not a simple force acting in isolation. It is a system. Every planet's gravity overlaps with every other's. The Sun dominates, but moons tug locally. Asteroids perturb trajectories. Even distant stars exert influence, however faint. Space is not empty. It is layered. This is why navigation is so complex. A spacecraft traveling through the solar system is constantly under the influence of multiple gravitational sources. Its path is not a smooth curve, but a constantly shifting compromise between competing pulls. This complexity is not noise, it is structure. Engineers exploit it. They design trajectories that intentionally pass through regions where gravitational influences align favorably. They aim for specific distances, angles, and arrival times, so that gravity does exactly what they want, when they want it. A spacecraft does not go to Jupiter. It arrives at Jupiter at a precise moment in Jupiter's orbit, at a precise speed and angle, so that Jupiter sends it somewhere else. This is why missions are planned decades in advance. Gravity does not wait. If you miss the alignment, the opportunity may not return for years, or ever. This reliance on gravity creates a profound constraint. Space travel is not just about where you want to go, but when you are allowed to go. Launch windows exist because planets move. A mission to Mars is not possible every day. It is possible only when Earth and Mars are aligned in a way that makes the journey efficient. Miss that window, and you may have to wait years. Gravity dictates the calendar. This is another way gravity asserts its authority. It does not merely shape paths, it schedules ambition. And gravity is indifferent. It does not care about budgets, politics, or human timelines. It moves planets according to mass and distance alone. Humanity must adapt or be left behind. This is why gravity is both enabling and cruel. A poorly planned gravity assist can destroy a mission as easily as it can save one. Arrive too close, and the spacecraft may crash or burn in an atmosphere. Arrive too far, and the assist is wasted. Arrive at the wrong angle, and the spacecraft is flung in the wrong direction. There is no forgiveness. There is only geometry. This unforgiving precision extends beyond planetary flybys. Gravity defines how spacecraft enter orbit, how they land, how they take off again. To orbit a planet, a spacecraft must match its gravitational rhythm. It must arrive at the correct speed, not too fast, not too slow. Too fast, and it escapes. Too slow, and it crashes. Orbit is not a place, it is a relationship, and gravity enforces that relationship relentlessly. This is why entering orbit around another world is one of the most dangerous moments of any mission. After months or years of coasting, everything comes down to a single burn. Miss it, and the spacecraft may never get another chance. Mars has claimed many victims this way. Spacecraft that arrived just a little too fast skipped off its atmosphere. Others descended too steeply and disintegrated. The difference between success and failure was measured in seconds and degrees. Gravity does not negotiate, but gravity can also be gentle if approached correctly. Atmospheric braking, for example, allows spacecraft to use a planet's atmosphere to slow down without fuel. By skimming the upper layers of air, a spacecraft converts kinetic energy into heat, shedding speed through drag. This is gravity-assisted braking. It is dangerous, but efficient. A spacecraft must dive deep enough to slow down, but not so deep that it burns up. Once again, the margin is thin. This reliance on gravity explains why space travel feels so fragile. Not because our technology is weak, but because we are threading needles at cosmic scales. And yet, gravity makes one thing clear: straight lines are the enemy. The shortest path in space is rarely the best one. Direct routes waste fuel. Curved paths conserve it. The universe rewards those who follow its contours. This is why space trajectories often look absurd to the untrained eye. They loop. They arc. They move away before moving closer. They feel inefficient because they are not designed for intuition. They are designed for physics. And physics is not concerned with comfort. Gravity also reveals a sobering truth about human limits. The solar system is navigable because gravity provides stepping stones. Planets allow us to borrow energy. Moons allow us to park, refuel, and redirect. But between stars, gravity thins out. Interstellar space is vast not just in distance, but in emptiness. There are no massive bodies close enough to provide useful assists, no convenient highways, no easy shortcuts. Between stars, engines matter again. Fuel matters. Energy matters. This is why interstellar travel is so daunting. It is not just far, it is unsupported. The solar system is a network. Interstellar space is a desert. This distinction matters. It explains why we can explore planets but not stars, why probes can roam but civilizations cannot yet migrate. Gravity makes local exploration possible. Its absence makes expansion nearly impossible. And this leads to the deepest implication of all. Gravity does not just move spacecraft, it shapes civilization. Where gravity wells are shallow, movement is easy. Where they are deep, movement is rare. Earth's gravity keeps us grounded. The sun's gravity keeps planets bound. The galaxy's gravity keeps stars in formation. Everything is arranged by mass. Human ambition operates within these arrangements, not above them. We do not choose routes freely. We negotiate them with gravity. We do not decide when to go. We wait for alignments. We do not dominate motion. We borrow it. This is why gravity is the real highway of space. Not because it is smooth or fast, but because it exists whether we want it to or not. Because it carries everything, including us. Because resisting it is expensive, but cooperating with it is powerful. Every successful mission is a lesson in humility. Every failure is a reminder that the universe does not care about intention. Gravity does not reward strength. It rewards understanding, and the more we understand it, the further we can go with less. But gravity also imposes a final constraint, one that no amount of cleverness can fully escape. Gravity shapes motion, but mass shapes gravity. And mass, once you carry it, becomes a burden that follows you everywhere, which is why the next barrier is unavoidable. Because no matter how elegant your trajectory, no matter how perfectly you ride gravity's highways, you are still imprisoned by one brutal truth. Fuel has mass, and mass punishes ambition. That is the tyranny waiting ahead. Every dream of spaceflight eventually collides with the same enemy. Not distance, not time, not even gravity. Fuel. Fuel is the invisible dictator of every spacecraft design, every mission plan, every ambition humanity has ever projected beyond Earth. It decides how far you can go, how fast you can travel, how long you can stay, and whether you can ever return. In space, fuel is not just a resource. It is a punishment, because fuel has mass, and mass makes everything harder. On Earth, this problem hides behind convenience. Cars carry fuel with little consequence. Airplanes burn it and shed weight as they fly. Rockets, however, reveal the truth brutally. To lift fuel, you need fuel. To carry that fuel, you need more fuel. And to lift that extra fuel, you need even more fuel. This recursive trap is known as the tyranny of the rocket equation. It is not a metaphor. It is a mathematical sentence passed down by physics, and it has never been overturned. The rocket equation states that the amount of velocity change, delta V, a spacecraft can achieve depends logarithmically on the ratio between its initial mass and its final mass. In simpler terms, if you want to go faster, you must carry exponentially more fuel. Not linearly, exponentially. This is why rockets look the way they do. Tall, fragile towers dominated by fuel tanks, with tiny payloads perched at the top like afterthoughts. The payload, the thing you actually care about, is often only a few % of the total launch mass. Everything else is fuel and structure to hold fuel. This is not inefficiency. This is inevitability. No engineering cleverness has ever escaped it. Better engines help. Lighter materials help. Smarter trajectories help. But none of them break the fundamental relationship. The universe has decided that moving mass is expensive. This is why spaceflight begins with violence. Rockets must produce absurd amounts of thrust just to escape Earth's gravity well. Not because Earth's gravity is uniquely strong, but because escaping a gravity well requires speed, and speed requires fuel. Earth demands about 11.2 kilometers per second to escape completely. Reaching low Earth orbit alone requires nearly 7.8 kilometers per second. When you include atmospheric drag and gravity losses during ascent, the real requirement climbs higher. Every one of those meters per second costs fuel, and that cost compounds. This is why most of a rocket's mass is discarded before reaching orbit. Stages fall away because empty tanks are dead weight. Keeping them would doom the mission. Spaceflight begins by shedding mass violently, like a snake shedding skin mid-motion. And this problem does not end once you reach space. In fact, it becomes worse. Because in space, you cannot refuel easily. There are no gas stations, no pipelines, no convenience stops. Every kilogram of propellant you will ever need must be carried from the start. unless you design something radically different. This reality shapes mission architecture more than any other factor. Engineers do not ask, where do we want to go? They ask, what delta V can we afford? Destinations are chosen not by desire, but by arithmetic. This is why some missions seem oddly indirect. A spacecraft may spiral outward slowly, rather than accelerating directly. It may use low-thrust engines over years, instead of high-thrust burns over minutes. It may rely on gravity assists obsessively. All of these strategies exist to minimize fuel expenditure, because fuel is the bottleneck. Chemical rockets, the dominant technology today, are particularly constrained. They rely on chemical energy released through combustion. This energy density is high by human standards, but pitiful by cosmic ones. Even the best chemical propellants convert only a tiny fraction of mass into energy. The rest is inert exhaust, expelled violently to produce thrust. This is why exhaust velocity matters so much. The faster you can throw mass out the back, the more efficiently you can accelerate forward. But chemistry has limits. No chemical reaction can exceed certain energy thresholds. That ceiling caps how efficient chemical rockets can ever become. Incremental improvements are possible, but revolutions are not. This means chemical rockets are near their theoretical maximum already, which leads to a sobering conclusion. Humanity reached space not because rockets became good, but because we reached the minimum threshold needed to brute force our way out of Earth's gravity. We are not far above that threshold. This fragility explains why launching anything heavy is so difficult. Space stations are assembled piece by piece because launching them whole would require absurd amounts of fuel. Deep space missions are stripped down to essentials. Redundancy is limited. Comfort is sacrificed. Mass is the enemy. This is also why crewed missions are exponentially harder than robotic ones. Humans require life support, shielding, food, water, air, and psychological stability. Every one of those needs adds mass. Every kilogram added demands more fuel, which demands more mass. The spiral tightens quickly. This is why sending humans to Mars remains so difficult, not because we do not know how, but because the fuel cost of doing it safely is enormous. Robotic probes can coast silently, shut down systems, tolerate radiation, and wait patiently. Humans cannot. Fuel must support not just motion, but survival. And then there is the return trip. Getting somewhere is hard, coming back is harder. A return journey doubles your fuel requirements, or more, unless you can refuel at the destination. Without in-situ resource utilization, missions become one-way by default. This is not philosophical, it is logistical. A Mars mission that plans to return astronauts must either carry return fuel from Earth or produce it on Mars. Carrying it from Earth multiplies launch mass dramatically. Producing it on Mars requires heavy equipment and flawless execution. Fuel dictates strategy, and fuel punishes hesitation. Because the longer a mission lasts, the more resources it consumes. Power systems degrade, supplies run out, radiation accumulates, psychological strain increases. Fast missions require high delta V. High delta V requires fuel. Fuel increases mass. Mass increases delta V requirements. The loop is vicious. This is why low-thrust propulsion systems, like ion engines, exist. They trade time for efficiency. Ion engines produce tiny thrust, but can operate for years, gradually building enormous velocity changes with very little fuel. They do not break the tyranny of fuel, but they negotiate with it. Ion engines work by accelerating ions to extreme speeds using electric fields. Their exhaust velocity is far higher than chemical rockets, meaning they get more momentum per unit of mass expelled. The trade-off is thrust. Ion engines cannot lift off from Earth. They are useless in gravity wells. But in the vacuum of space, over long durations, they are transformative. Missions like Dawn demonstrated this beautifully, visiting multiple asteroids using the same spacecraft, something impossible with chemical propulsion alone. But even ion engines depend on power. Solar panels weaken with distance from the sun. Nuclear sources add mass and political complexity. Power is not free. Every solution shifts the burden, never removes it. This is why the phrase fuel efficiency can be misleading in spaceflight. It suggests optimization within comfort. In reality, every mission operates near the edge of feasibility. Margins are thin because physics demands them to be. And then there is heat. Burning fuel produces not only thrust, but thermal stress. Engines must survive extreme temperatures and pressures. Cooling systems add mass. Materials impose limits. Everything cascades. This cascade explains why radical propulsion concepts, nuclear thermal rockets, fusion drives, antimatter engines, are so attractive. They promise higher energy densities, higher exhaust velocities, and freedom from chemical limits. But they come with new problems. Nuclear engines involve radiation shielding, political risk, and engineering challenges. Fusion remains experimentally elusive. Antimatter is fantastically expensive and dangerous to store. Each solution shifts the tyranny without abolishing it. Even hypothetical warp drives, if they exist at all, would require negative energy or exotic matter in quantities beyond imagination. Fuel, in some form, always returns. This is the central tragedy of space travel. The universe is vast, the distances are cruel, and energy is expensive. Humanity is not limited by imagination, it is limited by mass and momentum. And yet, despite this tyranny, spacecraft do travel. Probes cross billions of kilometers. Humans orbit Earth continuously. Space stations remain aloft for decades. This happens because engineers are relentless. They shave grams. They optimize trajectories. They accept risk. They exploit gravity. They stack probabilities in their favor. Spaceflight is not about overpowering physics. It is about surviving it. Fuel is not the villain because it is scarce. It is the villain because it multiplies itself. Every kilogram carried forward demands payment in advance, and this payment defines the boundary of our reach. Which leads to the next realization. If fuel is the chain that binds spacecraft to Earth, then the only way to go further is to break the assumption that fuel must be carried at all. And that thought, dangerous, revolutionary, and incomplete, is what drives the next phase of space travel. Not faster engines, not bigger rockets, but propulsion that does not rely on carrying propellant. Light, fields, momentum exchange, ideas that sound impossible until they don't. That is where this story goes next. The moment you accept that carrying fuel is the core limitation of space travel, the question stops being how to improve engines. It becomes something far more radical. How do you move without carrying reaction mass at all? This question has haunted propulsion science for more than a century. It is not a fringe idea. It is a logical consequence of the rocket equation. If fuel mass explodes exponentially with speed, then the only true escape is propulsion that does not require onboard propellant. This is where space travel stops looking like engineering and starts looking like philosophy. Because momentum must be conserved, because forces must come from somewhere, because nothing in the universe moves for free. And yet, there are loopholes, not violations of physics, but exploitations of it. The first loophole is light. Light has no rest mass, but it carries momentum. When photons strike a surface and reflect, they transfer that momentum. The force is tiny, but constant. This is the principle behind solar sails. A solar sail is exactly what it sounds like. A large, reflective surface that captures momentum from sunlight. Each photon pushes gently. Individually, the push is negligible. Collectively, over time, it becomes significant. Solar sails do not accelerate quickly. They accelerate patiently. Near the sun, the pressure from sunlight is strongest. A sail can gradually build velocity without burning a gram of fuel. As long as the sun shines, and it will for billions of years, the sail has propulsion. This changes the trade-off entirely. Instead of fuel versus mass, the equation becomes area versus time. Large sails catch more photons. Longer missions accumulate more velocity. The spacecraft becomes less like a projectile and more like a drifting seed. Japan's Ikaros mission demonstrated this concept successfully. The spacecraft deployed a sail only micrometers thick and used it to alter its trajectory measurably. No engines fired, no propellant consumed. This was not science fiction. It was navigation by light. But solar sails have limits. Light intensity decreases with distance from the sun. Beyond the outer planets, sunlight becomes too weak to provide meaningful thrust. The sail becomes a passive object, unless the light comes from somewhere else. This is where directed energy propulsion enters the picture. Instead of relying on sunlight, a powerful laser array could beam light at a sail from afar, pushing it to extreme speeds. In theory, this could accelerate tiny spacecraft to significant fractions of the speed of light. This is the idea behind concepts like Breakthrough Starshot. The logic is seductive. The spacecraft carries no fuel. The propulsion system stays behind. Acceleration happens externally. The mass problem collapses. But new problems emerge. Pointing a laser with extreme precision across millions of kilometers is non-trivial. Keeping the sail stable under immense acceleration is difficult. Deceleration at the destination is unsolved. Light can push you forward easily. Stopping is another matter. Still, the principle holds. Propulsion without onboard fuel is not impossible. It is merely inconvenient. Another loophole lies in magnetic fields. Space is not empty. It is threaded with magnetic fields generated by stars, planets, and the galaxy itself. Charged particles, like those in the solar wind, stream through these fields continuously. If a spacecraft could interact with this flow, it could extract momentum. This is the idea behind magnetic sails and electric sails. Instead of a physical surface, these systems deploy electromagnetic fields that deflect charged particles. Each deflection transfers momentum, producing thrust. Once again, the thrust is small but continuous, and once again, no fuel is required. These systems blur the line between propulsion and environment. The spacecraft becomes a kind of parasitic organism, feeding off ambient energy flows. But like solar sails, these methods depend on conditions. Solar wind weakens with distance. Magnetic fields vary unpredictably. Control is difficult, reliability is uncertain, and yet the appeal is undeniable. Then there is perhaps the most elegant loophole of all: momentum exchange. Imagine two objects connected by a tether in orbit. One dips lower into a gravity well, gaining speed. The other is flung outward, gaining altitude and velocity. This principle underlies tether propulsion and space elevators. A space elevator, in its purest form, would allow payloads to climb into orbit without rockets. Energy would be supplied electrically from the ground. The payload would not carry fuel. It would ride infrastructure. This would shatter the tyranny of fuel at launch. But space elevators demand materials with extreme tensile strength, far beyond what we can currently manufacture at scale. Carbon nanotubes hint at possibility, but engineering reality lags theory. Tethers in orbit, however, are more achievable. They can exchange momentum between spacecraft, boosting some while slowing others. Once again, fuel is replaced by cleverness. Even more radical ideas exist. Nuclear propulsion, for instance, does not eliminate fuel, but it changes its nature. Nuclear thermal rockets use nuclear reactors to heat propellant directly, achieving higher exhaust velocities than chemical engines. Nuclear electric propulsion uses reactors to generate electricity, powering ion engines with far greater endurance. These systems reduce fuel mass dramatically for deep space missions, but they introduce complexity, radiation risks, and political resistance. Fusion propulsion promises even more. If controlled fusion could be achieved reliably, spacecraft could tap energy densities far beyond chemical limits. Exhaust velocities could reach extraordinary levels. But fusion remains elusive. Every breakthrough seems to recede just beyond reach. Antimatter sits even further out. Matter-antimatter annihilation converts nearly 100% of mass into energy. In principle, it is the ultimate fuel. In practice, antimatter is fantastically difficult to produce, store, and control. A gram of antimatter would release energy equivalent to a nuclear bomb. The tyranny of fuel is replaced by the tyranny of containment, and beneath all of these ideas lies a deeper truth. Every propulsion method, no matter how exotic, must obey conservation laws. Momentum must be balanced. Energy must be supplied. Entropy must increase. There are no miracles, only trade-offs. This is why even speculative concepts like warp drives remain controversial. They require exotic matter with negative energy density, something not known to exist in usable quantities. Physics does not say they are impossible. It says they are unpaid for, and the bill is enormous. So where does this leave humanity? Trapped, but not motionless. Within the solar system, clever use of gravity, low-thrust propulsion, and external energy sources can take us far. We can explore, we can build, we can learn. But expansion beyond that, to true interstellar travel, remains constrained not by courage or intelligence, but by energy economics. The universe is not hostile, it is expensive, and fuel is the currency. This reality reframes every conversation about space colonization, starships, and galactic empires. It reminds us that civilizations are shaped not by dreams, but by logistics. A species that cannot move mass cheaply, cannot spread easily. A species that cannot shed its dependence on onboard fuel remains local. This is not pessimism, it is clarity, because clarity reveals the path forward. The tyranny of fuel is not absolute, it is contextual. It binds us now because our infrastructure is primitive. We launch everything from deep gravity wells. We discard hardware. We reinvent propulsion every mission. But infrastructure changes equations. Fuel depots in orbit, manufacturing in space, mining asteroids, power generation away from Earth. Each of these reduces the burden. Each shifts mass off the launch stack. Each weakens the tyranny. The history of transportation on Earth followed the same arc. Early explorers carried everything with them. Later, they built roads, ports, and supply chains. Space is no different. The difference is scale, and scale punishes delay, which leads to the final, unavoidable realization. Space travel is not a single problem. It is a system problem. Propulsion, energy, materials, timing, gravity, and human limits all intersect. Fuel is merely the pressure point where all these constraints meet. To move beyond it, humanity must stop thinking in missions and start thinking in ecosystems. Because the universe will not bend for isolated efforts. It only yields to sustained presence. And that, more than engines or equations, is the true challenge waiting ahead. Imagine standing at the edge of a dark ocean, knowing there is a distant shore, but no waves, no wind, and no landmarks. You cannot swim in a straight line. You cannot even see the coast. Every movement is dictated by invisible currents, by the pull of unseen forces, by the precision of your starting point. This is the reality of navigating space. Navigation in space is not like driving a car, piloting a boat, or even flying an airplane. On Earth, you can look, sense, correct, and repeat. You can see the road, the horizon, the landmarks. In space, none of this exists. The road is invisible, defined by the gravitational dance of planets, moons, and stars. Landmarks are points of light separated by millions of kilometers. Motion is invisible. Time is delayed. Every command must be sent in advance. Every correction anticipated. Every error calculated before it occurs. And yet, humanity has learned to navigate this void, not by instinct, not by luck, but by mathematics, physics, and the patient art of prediction. At the heart of this art is trajectory planning. Every spacecraft starts its journey with a plan, a path defined in 6 dimensions, 3 of space, 3 of motion. Engineers calculate the initial velocity, the angles, the burn sequences, and the gravitational encounters that will carry the spacecraft from its starting point to its destination. Every kilogram of mass, every joule of energy, every delay in timing matters. The trajectory is not just a line on a map. It is a living plan that will dictate every moment of the journey. Consider interplanetary travel. A spacecraft departing Earth cannot aim directly at Mars, as a child might imagine. Planets move constantly. Earth rotates around the Sun. Mars rotates faster or slower, its orbit eccentric and inclined. A direct line is meaningless. Instead, engineers calculate transfer orbits, elliptical paths that intersect the target's future position. The spacecraft must arrive not where the planet is now, but where it will be months or years later. Timing is everything. A missed launch window can delay a mission by years. This is why space agencies obsessively calculate planetary alignments. They do not merely plan a course, they plan a cosmic rendezvous. Trajectory planning is also about compromise. A spacecraft can reach its destination faster with more fuel, but this adds mass and complexity. Slower journeys conserve fuel but increase mission duration and risk. Engineers must balance speed, efficiency, safety, and cost. Every choice echoes across millions of kilometers for years at a time. There is no trial and error in space. Once launched, a spacecraft cannot pause and rethink. Every decision must be made in advance. Even in low Earth orbit, navigation is a delicate dance. Spacecraft orbit Earth at thousands of kilometers per hour, yet the tiniest velocity change can alter the orbit drastically over time. A small burn, lasting seconds, can raise or lower an orbit, change inclination, or synchronize with the International Space Station. These maneuvers require meticulous calculation, precise execution, and constant monitoring. Even the most minor misalignment can escalate into a catastrophic miss. The challenge intensifies as distances grow. Farther from Earth, communication delays increase. Signals to Mars take between 4 and 24 minutes to arrive, depending on relative positions. By the time an operator on Earth sees a problem, it may be too late to correct it directly. Spacecraft must operate autonomously, guided by pre-programmed commands and onboard sensors. Navigation becomes a combination of prediction and self-correction. The spacecraft itself becomes a pilot, interpreting data and executing maneuvers with minimal human intervention. One of the most important tools for navigation is gravity itself. As discussed in the previous section, gravity can accelerate, decelerate, and redirect spacecraft. Engineers use gravity assists to reach distant targets with minimal fuel, but harnessing these invisible highways requires exquisite precision. A spacecraft approaching Jupiter at the wrong angle might miss the planet entirely, or worse, be flung into deep space at a trajectory it cannot recover from. Gravity is a friend and a hazard, and understanding its influence is the essence of cosmic navigation. Navigation also relies on reference points, distant stars, pulsars, and planetary positions. On Earth, a navigator might rely on landmarks or GPS satellites. In space, the stakes are higher and the tools are subtler. Star trackers measure positions against a catalogue of distant stars. Pulsar timing can provide navigation akin to a cosmic lighthouse. Sensors must account for parallax, light travel time, and the motion of celestial bodies. Even tiny errors in reference points can propagate into massive deviations over millions of kilometers. As missions grow in ambition, navigation becomes a multi-layered challenge. A spacecraft heading to the outer planets must account for the Sun's gravity, the gravitational influence of moons and planets along the way, and the perturbations caused by asteroids or interplanetary dust. It must maintain orientation for solar panels, antennas, and instruments. It must manage heat, radiation, and the drift caused by onboard fuel consumption. Every factor interacts with every other factor. Navigation in deep space is not a linear problem. It is a dynamic, multi-dimensional puzzle that evolves continuously. The complexity is further compounded by human psychology. mission planners must imagine events years in advance, anticipating scenarios that may never occur. They must plan for contingencies, redundancies, and failures that cannot be physically tested. Spacecraft cannot be relaunched if something goes wrong. Every aspect of navigation, trajectory, velocity, timing, orientation, must be meticulously simulated before launch. Every miscalculation has consequences that amplify across distance and time. Consider the Voyager missions. Launched in 1977, these spacecraft were sent to explore the outer planets and eventually enter interstellar space. Their trajectories were carefully timed to exploit a rare alignment of Jupiter, Saturn, Uranus, and Neptune. A direct path would have required enormous fuel and been impossible. Instead, mission planners used a complex chain of gravity assists. The spacecraft slingshotted from planet to planet, accelerating without consuming fuel. Every maneuver had to be executed within seconds, with years of coasting between adjustments. Voyager 1 and 2 are still traveling today, decades beyond their original missions, following paths calculated before most of the engineers were even adults. Navigation is not merely technical, it is strategic. Engineers must predict not only physical trajectories but also mission priorities, potential obstacles, and environmental hazards. Space is full of unseen threats. Micrometeoroids, radiation, debris, and unpredictable solar activity. Even minor variations in solar wind or planetary magnetic fields can alter the path of a spacecraft over time. Navigators must anticipate these forces, compensate in advance, and design trajectories that are robust against uncertainty. Autonomy is key. Modern spacecraft often carry onboard systems capable of detecting anomalies, calculating corrections, and executing maneuvers without waiting for Earth-based instructions. The Mars rovers, for instance, navigate the surface semi-independently, analyzing terrain, avoiding hazards, and choosing paths that optimize both safety and scientific output. In interplanetary travel, autonomy is even more critical. The farther a spacecraft travels, the longer the communication delay, and the more it must rely on pre-programmed intelligence. But even with the most advanced technology, navigation is always constrained by physics. The fastest route is rarely a straight line. The most efficient path is a compromise between time, energy, and safety. Trajectories may loop around planets, follow complex curves, or co-opt gravitational assists. They may involve extended periods of coasting, precise burns, and continuous monitoring. Navigation is not a matter of brute force. It is an art of anticipation, precision, and patience. This art has broader implications for space exploration. It demonstrates that humanity cannot simply push its way into the cosmos. Expansion is governed by physics as much as ambition. Every new mission, every new target, requires understanding not only where we want to go, but how the universe will allow us to arrive. Navigation is negotiation with reality. The spacecraft is not a conqueror, it is a student, learning to read the invisible currents of gravity and motion that shape the solar system. The history of navigation in space is also a story of adaptation. Early missions relied on Earth-based tracking, radio signals, and visual cues. As distances grew, new techniques emerged: inertial measurement, star tracking, pulsar timing, and autonomous navigation. Each innovation extended our reach, allowing spacecraft to venture farther, move faster, and survive longer in the void. Navigation is iterative. Every success builds confidence, every failure teaches lessons, and every mission advances the art. In addition to reaching destinations, navigation shapes mission design. Engineers must decide not only how to get there, but also when, how, and why. Timing determines launch windows. Trajectories influence payload design and fuel allocation. Orientation affects communications, power generation, and thermal management. Navigation dictates everything from instrument placement to antenna pointing, from mission duration to contingency planning. It also influences risk management. Navigators must plan for worst-case scenarios, engine failures, communication loss, or unexpected gravitational anomalies. They must ensure that even in failure, the spacecraft can continue its mission, or at least survive. This foresight transforms navigation from a technical task into a discipline of foresight, judgment, and resilience. The challenges of navigation are compounded when human crews are involved. Astronauts rely on precise trajectories for life support, radiation shielding, and mission timing. Course corrections are no longer abstract, they are matters of survival. Even minor deviations in trajectory can jeopardize return windows, expose crews to prolonged radiation, or consume critical resources. Navigation becomes a question of human endurance, psychology, and judgment. Finally, navigation is intimately tied to the concept of coasting, explored in earlier sections. Every trajectory includes vast stretches where the spacecraft does nothing but drift. These periods of silence are active in their own way. The spacecraft follows the laws of motion, obeys gravity, and accumulates velocity. Navigation ensures that these passive phases are aligned with mission objectives, that coasting becomes an opportunity rather than a risk. Precision in planning allows the universe to do the work, while the spacecraft simply moves along invisible highways. In the end, navigation is the art of moving through a universe that is indifferent, precise, and unforgiving. It is the interplay between ambition and physics, between planning and patience, between prediction and adaptation. Every journey, from low Earth orbit to the outer planets, depends on it. Every success, from Voyager to modern probes, demonstrates mastery over the invisible currents of space. And every failure reminds us that the void is impartial, punishing errors and rewarding foresight. Understanding navigation is understanding the cosmos itself. It is learning that motion is not just about engines, fuel, or thrust, but about harmony with forces that cannot be ignored. It is recognizing that space travel is a dialogue with gravity, time, and distance, a conversation conducted in numbers, angles, and velocities. And it is realizing that the farther we wish to go, the more this dialogue defines our limits, our strategies, and our future. Navigation is not merely a technical skill. It is the poetry of motion, the negotiation of mass, momentum, and time, the art of turning the void into a passage, and the deeper humanity understands it, the farther we can reach. For over half a century, humans have relied on chemical rockets to leave Earth. These towering machines, burning fuel with violent energy, have launched every satellite, probe, and human into space. They are powerful, proven, and brutally effective. And yet they are also painfully limited. Chemical propulsion is bound by energy density. Every kilogram of fuel you carry adds mass. Every kilogram of mass requires more fuel. The rocket equation, which has governed spaceflight since Tsiolkovsky, remains unforgiving. The farther you wish to go, the more the mass grows, and the more fuel you must carry. Reaching distant planets becomes an exercise in compromise. Reaching the stars becomes, for all practical purposes, impossible. But humans are not easily deterred. We have a habit of looking at limits and asking how to bypass them. The future of propulsion lies not in burning more chemicals, but in breaking the chains of traditional fuel altogether. It lies in harnessing energy that is external, abundant, or vastly more efficient. It lies in concepts that, for decades, existed only in the minds of dreamers and physicists. And yet, step by step, they are becoming engineering problems, not just thought experiments. The first major innovation beyond chemical propulsion is nuclear thermal propulsion. Here, the fuel is not burned chemically. Instead, it is heated by a nuclear reactor, and the hot propellant is expelled to produce thrust. By replacing chemical reactions with nuclear energy, exhaust velocities increase dramatically. Missions that would require years with chemical rockets could, in principle, be shortened significantly. Nuclear thermal rockets have another advantage: efficiency. They provide more thrust per unit of fuel. This is critical when moving massive payloads across the solar system. Mars missions, for instance, could benefit immensely. With nuclear thermal propulsion, transit time could drop from months to weeks. Shorter missions reduce radiation exposure, lower resource demands, and increase safety margins for human crews. However, nuclear propulsion is not without challenges. Reactors must operate safely in the vacuum of space. They generate extreme heat. Shielding must protect both the spacecraft and its crew from radiation. Launching nuclear material from Earth introduces political, safety, and environmental concerns. Yet despite these obstacles, the United States and other agencies have tested prototypes. The concept is mature enough to be deployed if the political and engineering hurdles can be overcome. If nuclear thermal rockets promise brute strength, ion engines demonstrate patience and efficiency. Ion engines do not rely on explosive force. They ionize propellant, commonly xenon, and accelerate the ions using electric fields. The thrust produced is tiny, often less than a newton, but it can be applied continuously for years. Over time, the spacecraft accumulates incredible speed, far exceeding what chemical rockets can achieve with comparable fuel. Missions like NASA's Dawn spacecraft proved the viability of ion propulsion. Dawn visited both Vesta and Ceres in the asteroid belt, performing complex orbital insertions and departures that would have been impossible with chemical engines alone. Ion engines allow spacecraft to linger, adjust trajectories, and execute intricate maneuvers with minimal fuel consumption. They are, in essence, the long-distance runners of space propulsion, slow to start, but capable of unprecedented endurance. Ion propulsion also dovetails with nuclear energy. A nuclear reactor can supply electricity to ion engines, combining the high energy density of nuclear fuel with the efficiency of electric propulsion. The result is a system capable of sustaining deep space missions for years without refueling, a critical requirement for interplanetary and interstellar probes. Beyond engines that expel propellant, a radically different form of propulsion emerges: the solar sail. As discussed, light carries momentum. Each photon that strikes a reflective surface transfers a minute push. Over time, this push accumulates into measurable acceleration. A spacecraft equipped with a large, ultra-thin sail can, in principle, reach significant fractions of the speed of light, entirely without carrying fuel. The principle is deceptively simple, but execution is delicate. The sail must deploy flawlessly, maintain structural integrity, and orient precisely to optimize thrust. Even minor misalignments can reduce efficiency or destabilize the spacecraft. Despite these challenges, Japan's Ikaros mission successfully demonstrated solar sail technology, proving that light itself can propel humanity's machines across the void. The advantage of solar sails is not speed alone, it is sustainability. Unlike chemical rockets, they are not limited by onboard fuel. They offer continuous acceleration as long as the spacecraft remains within the influence of a star, or potentially a directed laser beam. Over decades, even minuscule forces produce extraordinary velocities. Building on solar sail concepts, laser propulsion represents a leap toward interstellar ambition. Instead of relying on sunlight, a powerful ground or orbit-based laser could beam energy directly at a spacecraft, accelerating it to extreme speeds. Tiny probes could, theoretically, reach Alpha Centauri in decades rather than millennia. The physics is straightforward. The laser transfers momentum via photons, pushing the craft without the need for onboard propellant. The engineering, however, is staggering. The laser must maintain precise focus over millions of kilometers. The sail must withstand intense radiation pressure without tearing. Deceleration at the target is an unresolved problem. Yet the promise is profound. Propulsion becomes external, breaking the tyranny of fuel entirely. Laser-driven sails also introduce new strategic considerations. Launching a probe becomes a matter of infrastructure, not onboard energy. A single laser installation could accelerate hundreds of small probes, distributing humanity's presence across interstellar distances without refueling. It shifts the paradigm from individual spacecraft carrying everything to global, or even planetary, scale energy investment. Another hybrid concept is nuclear electric propulsion, which merges nuclear reactors with ion or plasma engines. Here, a reactor generates electricity to power high-efficiency propulsion systems. The advantage is twofold. The spacecraft achieves high exhaust velocity and can operate for extended periods without refueling. Nuclear electric systems are particularly suited for deep space missions. Communication delays with Earth may stretch years. Crews must make autonomous decisions with permanent consequences. Generations may pass before the ship returns, or Earth may change beyond recognition. Designing environments that preserve mental health is as vital as supplying air or water. Light cycles, recreation, social structures, and meaningful work all contribute to maintaining sanity over unimaginable distances. Water, air, and food cannot be resupplied regularly on interstellar missions. Systems must recycle nearly everything. Closed-loop life support is not optional. It is mandatory. Water must be filtered, purified, and reused. Oxygen must be generated from electrolysis or chemical reactions and balanced against CO2 removal. Food production becomes a complex challenge, possibly requiring hydroponics, aquaponics, or synthetic nutrition. Every system interacts. Waste becomes resource, and efficiency becomes survival. Early prototypes exist. The ISS operates partially closed loop, recycling water from humidity, urine, and condensate. Oxygen is generated via electrolysis of water. Food, however, is still largely pre-packaged. For deep space or colonization missions, self-sufficiency must be nearly perfect. Systems must be redundant, repairable, and adaptable to failure. There is no backup Earth. Earth gravity is more than comfort. It is biology itself. Without gravity, humans experience muscle and bone degeneration. The heart, lungs, and circulation adapt in ways that create long-term health risks. Long-term missions may require artificial gravity through rotation, centrifugal force, or constant acceleration. Rotating habitats offer one practical solution. A cylindrical or ring-shaped ship spinning on its axis generates centrifugal force that mimics gravity. The speed of rotation, radius of the habitat, and distribution of mass must be finely tuned to avoid motion sickness or structural stress. It is engineering married to biology, a direct acknowledgement that survival is not just about reaching the destination, but maintaining the human form along the way. Surviving in space is one thing. Colonizing other worlds is another. Mars, for instance, presents a partial atmosphere, extreme cold, dust storms, and low gravity. Humans cannot simply step onto its surface. Habitats must shield against radiation, provide pressurized and heated living space, and support closed-loop life systems. Farming requires indoor agriculture, hydroponics, and careful management of nutrients. Water may be extracted from ice or chemically produced. Terraforming remains science fiction at this scale, but small-scale, self-sufficient colonies are theoretically possible. Lunar colonies present similar but distinct challenges: vacuum, extreme temperature swings, and micrometeoroid impacts. The Moon's lower gravity creates long-term physiological issues similar to Mars, though distances from Earth are much shorter. Lunar bases could serve as training grounds for deeper missions, testing closed-loop systems, energy generation, and social structures under extreme conditions. Long-duration missions and colonies require more than technology. They require social engineering. Who governs a starship? How are conflicts resolved? How is labor distributed when every human action affects survival? Isolation can exacerbate inequality, competition, and mental strain. Cohesion becomes a survival mechanism. Historical analogues exist in submarines, Antarctic stations, and long-term naval missions. These teach that trust, training, and redundancy in leadership are crucial. But interstellar missions amplify the stakes exponentially. A single failure in governance, communication, or morale can end the mission. human factors are as limiting as propulsion or life support. In space, resources are finite and precious. Energy must be harvested efficiently from solar panels, nuclear reactors, or future fusion sources. Materials must be recycled meticulously. Waste management becomes both a health necessity and a strategic concern. Colonies cannot rely on Earth to send supplies over years or decades. Sustainability becomes an ethical imperative, an engineering requirement, and a philosophical challenge. The economics of space survival extend beyond technical feasibility. Every kilogram of mass launched, every joule of energy spent, must be justified. Resource allocation becomes strategic. Propulsion, life support, research, and habitation must all be balanced. Scarcity is not theoretical, it is immediate. Space is a mirror that reflects inefficiency, punishes waste, and rewards foresight. Long-term survival and colonization depend on energy independence. Solar energy is effective within the inner solar system, but diminishes rapidly with distance. Nuclear power, including fission and fusion, offers higher energy density and consistent output. Propulsion, life support, and habitat energy must be integrated into a unified system. Every decision, thrust, trajectory, lighting, heating, water recycling, interacts with energy availability. The challenge is not just survival, but optimization across decades or centuries of operation. Despite the challenges, humanity has always looked outward. Colonies on Mars or the Moon represent the first steps in becoming a multiplanetary species. Each step is a lesson: closed-loop systems, radiation shielding, artificial gravity, autonomous governance, and resource management. These small steps prepare us for the distant stars, where timescales stretch, resources are even scarcer, and isolation is complete. Expansion beyond Earth is not optional. It is a long-term strategy for survival. Earth is vulnerable. Asteroids, pandemics, climate change, and human conflict are all existential threats. Spreading humanity across multiple worlds reduces risk, ensures continuity, and transforms civilization into a species capable of enduring cosmic timescales. Colonization is not mere ambition, it is insurance. Colonizing other worlds raises profound questions. Do we alter ecosystems or terraform planets? What rights do future generations have when missions span centuries? How do we balance survival, exploration, and stewardship? These are not theoretical concerns. They are immediate considerations that shape engineering, policy, and planning. Space colonization forces humanity to confront its responsibilities, not just its capabilities. Robots and AI will precede, accompany, and support human expansion. Autonomous systems can build habitats, mine resources, and manage life support with precision and reliability. They reduce risk to humans and act as force multipliers for limited crews. In interstellar travel, AI may outlive human passengers, managing systems over centuries. Robots may become the first explorers of new stars, paving the way for eventual human settlement. Human culture will inevitably evolve off-Earth. Societies in closed habitats will develop new norms, rituals, and structures. Language, art, governance, and values may diverge from Earth's trajectory. This is not hypothetical. It is already observable in long-duration missions and isolated communities. The farther humanity travels, the more we become a multi-planetary, multi-societal species. Space is not just a frontier, it is a mirror reflecting adaptation, resilience, and creativity. The journey from Earth to the stars is not defined by speed alone. It is defined by survival, adaptation, and foresight. Propulsion, navigation, and trajectory enable movement. Life support, psychology, and social engineering enable survival. Energy, sustainability, and resource management enable endurance. Together, they define the conditions for humanity to endure beyond Earth. Colonization is both challenge and opportunity. It transforms technology into strategy, survival into society, and exploration into culture. The stars are not simply destinations, they are laboratories for the evolution of civilization itself. Humanity's ability to thrive in space will define our species for millennia. Every spacecraft, every habitat, every probe is a step in this journey. Every experiment, every failure, and every innovation teaches lessons about endurance, adaptability, and the limits of imagination. The cosmos is vast, indifferent, and unforgiving. Yet it also offers boundless possibility. Survival in space is the ultimate measure of human ingenuity, ambition, and resilience. The first steps have been taken. Rockets that escape Earth, habitats that sustain life, probes that reach distant worlds. The next steps are far more profound. Interstellar ambition, permanent colonization, and the creation of civilizations that endure across planets, decades, and centuries. The path is daunting, but the rewards, survival, expansion, and discovery are unmatched. Humanity is no longer bound solely to Earth. We are beginning to learn what it means to live among the stars, to adapt, endure, and expand. The challenges are immense, but the potential is even greater. Our future as a spacefaring species depends on understanding the void, respecting its laws, and daring to move forward despite them. The universe waits. Humanity must rise to meet it.